With the present image here about combustion scaling in the horizontal direction now. We were discussing the vertical direction and horizontal direction. And I said in the horizontal direction, it's mostly a diffusive movement in the bed. The problem that we have been mentioned many times is that when the fuel is added from the side, it has to be spread across the cross section, and the only remedy that you could have is to have several feed points, and you would like to know how many feed points are needed, and also how far will the fuel spread on the various conditions. This can be calculated, of course, with numerical methods, but it can also be estimated by simplified scaling approaches. So this is what I want to illustrate here. We have the air is always added from below in even over the cross section. Fuel is added here in a point, perhaps with some initial velocity, but basically, if you see it from above, it enters here and then it spreads. In this case, I assume that it is spreading isotropically, is spreading equal in all directions, because I have no other information in the modeling. The modeling is like this. We use the relationships that we have been discussed previously. We have the volatilization, char combustion, and then we are interested in the dispersion. The volatilization time has been, I have said it could be expressed in a rather simple way, related to the diameter of the particle to some power. For large particles, it was a little less than 2, and for small particles, maybe 1. And this is a coefficient simply. The char combustion time can be calculated in many ways, depending on the mode of char combustion. One of the simplest modes that I have illustrated before is when we have diffusion control, external diffusion control of the particle. And then I have derived this expression. So let us use this. Of course, the time of combustion of the char may also depend on kinetics and so on. And then the expression becomes more complicated, but it is possible to replace this equation with an adequate equation for the particular case that you are studying. So, but this is just for simplicity. I take this because I have derived it before. Now, this is the Einstein equation, which David referred to in his presentations. It gives the dispersion time as a function of the distance and the dispersion coefficient in the horizontal direction. This, of course, is an abuse of Einstein's expression to use it here, because this was derived for molecular interactions in a gas, and it was then isotropic and stochastic. But I say here it is not fulfilled completely in the fluidized bed. Nevertheless, we use it just being aware of this fact that we have to be careful, and we can add our derived diffusion coefficients from some literature on fluidized bed, but otherwise the form of the expression is very approximative when applied to fluidized bed. So, but the result then is very simple. We have the Damm-Curler number for the volatiles, the dispersion of the particle, fuel particle, related to the devolatilization time, and the Damm-Curler number for the char, the same dispersion time related to the time of combustion of the char. This is all. So what I do is that I take these previous expressions and I put them here, and then I can plot those two relationships in a diagram of Damköhler number, logarithmic scale here, and another logarithmic scale here, and I get then this curve or this line for volatile relationship, and this time this curve for char. And now we know that the Damköhler number, if it is below unity, it is reasonably even. If it is above, it is a maldistribution. So let's see what we get. If we have a certain size here, certain length of the reactor, for instance, if we have a certain dimension of the reactor, and this so just to give an example, if it is 1, it is the size divided by the particle diameter, but it is up to the cubic 1000 divided by 1000. So if 1 is particular reactor size, then we realize that the char combustion may be even. This is no problem with the char combustion. But if we come to the volatile for this situation, it is a maldistribution. Of course, we knew that already, even the first day of our first lectures. We were discussing the unevenness of the volatile release, but here it is illustrated how it is. So it is easy to realize that it is the fact. And here, in this case, we can also manipulate the parameters. We can check what happens if we have another gas concentration, and what happens if we have other particle sizes. Particle sizes included here and here. If we have a much larger size of particles, then these lines would be displaced yeah, they would be displaced here, and for the same size of reactor, we would have an even distribution if these lines are displaced towards the right. So we can by changing the parameters, we can easily see what happens in different situations. Of course, this is approximative, but it gives you an idea and what you can kind of confirmation of what you can believe, that when you change the particle size, of course the char combustion time will be longer and the volatilization time will be longer. But if the dimension of particle is not included here, then this is the same. So both these times are longer, and that means that combustion has the possibility to spread out in a longer distance, and then you have a better distribution of fuel. You can ask yourself, how about if I have a more reactive or less reactive fuel? It's not included here because we have assumed a diffusion limited case. But if we had considered some other case and we had included also the more complete considerations, then we could also have studied the influence of kinetic versus diffusion control char combustion. So this is quite simple but useful use of Damköhler numbers. I have another example, and this is taken from a company which is the name was Tampella. Now it is Valmet. It was in the United States actually. They built boilers for coal combustion, But before they delivered a boiler, they investigated the various things, among others, the sulfur capture capacity of various limestones. The point is that when a customer buys a boiler somewhere, he would like to use the local limestones because you don't want to transport the limestones very far. But limestones are very different from each other. So therefore, the manufacturer that want to be on the safe side and who doesn't want to promise too much, tests his limestones in the laboratory device. And that is a small reactor that they had in their laboratory, where they tested all the limestones that could be of interest. And then one of them were used for the proposal to build the boiler. When they later, a year later or so, put the boiler into operation with this limestone, they could check the ability of sulfur capture with this particular limestone. But the general experience was that the large plants always performed worse when the laboratory scale plant than the laboratory scale plant. Limestone performance to capture sulfur was much better in the laboratory than in a large plant. This difference was less for low volatile coals. That was their general experience. And I think then the result can be explained in terms of the Damköhler numbers by the spread of the fuel in the furnace to meet oxygen. But you have to also know what I have not told you so far. That is, the sulfurization needs oxygen. So if you have an oxygen-starved situation, the sulfurization will be very bad. It will not work, or it will even release some of the sulfur that is captured already. So if we have a situation like this, we have oxidizing. No, we have perhaps all the oxygen has been consumed here. There are oxygen outside here, but the problem then is that the sulfur is released during the devolatilization or partly during the combustion of the fuel. So it may be released where the amount of oxygen is not sufficient. And that is not so noticeable in a small plant, but it is noticeable in a large plant. And it is exactly what this diagram says, that in a small plant you are usually in the even distribution situation, whereas in a larger plant you have more. It's more likely that you have a maldistribution. And the results from the large plant were seen here by their measurements. The SO2 concentration. First, I should say that the axis. This is the distance from the front wall, and fuel, of course, was added at the front wall, and these are concentrations. So what you see here is the peak of sulfur concentration in this region, 1 meter from the front wall, but then further away the sulfur concentration was low. The same thing with the oxygen. There was no oxygen here, but only at some distance from the fuel injection point you have an excess of oxygen. This was below the secondary air injection point, and this was above the secondary air injection point. So you could see that you had an excess of air here, which is of course according to the design. And then the sulfur capture was okay, but it was not okay in this area where you have a deficit of oxygen. And this was seen in the large reactor, but in the small reactor, because of its size, there was not so it was not so noticeable. So this is another example of the scaling performance, what happens in scaling. Yeah, now I come to something that I have mentioned before, but this is some kind of background. We have been discussing this before, so it is to some extent a repetition. We use the damp color number in the vertical direction, and it is just as I have said before, where you have the vertical distance, the height of the reactor here, the fluidization velocity here, and the inlet concentration. So we have been talking about the number of the particle residence time. First of all, it is the height of the reactor divided by the velocity gives the gas residence time at least, and the particle residence time depends on the particle velocity, which is a little less than the gas velocity, and also on the number of turns that the particles have made through the cyclone. So it depends on this circulation number of the cyclone. You remember the circulation number was related to the efficiency of the cyclone, which in turn was related to the particle diameter. So we have this thing that determines how many times a particular particle size can circulate. And I didn't say it yesterday, but I showed this efficiency curve. If the particles are large, efficiency is always unity, so the particles don't escape. They just circulate. N is infinite, and there is no problem with combustion. But when the size of the particle becomes smaller, it is the efficiency is less. And this curve, the location of this curve in relation to the particle size distribution is determined by the cut size, the average particle size. And for cyclones of different efficiency, the cut size is different. So if you design a very efficient efficient cyclone, this curve is displaced towards the smaller sizes. If the cyclone is inefficient, the curve is displaced towards larger sizes like this. So the cut size tells us directly is a sign of the efficiency of the cyclone. It's written here. So it is expressed by this equation, but it can also be seen directly, as I pointed out. And of course, the efficiency, the total efficiency is the sum of all efficiencies, local efficiencies. I can sum it over all particle size fractions. And the mass of one particle size fraction has this efficiency. And then I can sum all these and I divide them by the total mass. So I get the total efficiency. But here we have the local efficiency, and it can simply be translated into a total efficiency. Everything depends on the cut size. So in these diagrams that I've shown you before, there were two parameters that were important to have a suitable damp color number, and that was either the height of the riser. This was the parameter of the height of the riser here. When it was a tall riser, the time of the residence time was large, and in fact it depends also on the cut size of the cyclone. In this case it was 27, so it was locked, but the parameter varied was the size of the cyclone, and then the corresponding residence time of a particle for one turn. And this determines then how many turns a certain particle of a certain size can do. Here, as I have said before, instead we have the cut size of the particles of the cyclone as a parameter, and the length of the cyclone of the furnace was 30 meters, and we get this set of curves. The smaller the cut size, the more efficient the cyclone, and the more we are in the preferable range of Damköhler numbers. With a longer or the larger cut size, of course, we have a certain region here where the particles will not be well captured or reacted. So this is also an example of a simple way of using such relationships, only that you know something about the cut size of the cyclone and the performance of the cyclone, which is not so easy to find out, but parameter studies can be made, at least. I'm not happy about this chapter about cyclone scaling, and I'm not happy about the following chapter about bed scaling either, but I will refer to it very superficially if you accept it, I hope, because I noticed that there are so many factors that require more explanations, and I have not wanted to go into this particular field to explain everything too much. What I can say is that the cyclone efficiency is influenced by many parameters like the particle properties, the solids concentration, the gas properties, the cyclone configuration, the inlet, the barrel diameter, which I will use. D is here, it's the barrel diameter. The entrance configuration, the vortex finder, and so on. All the details of the cyclone may influence the efficiency. But often it is possible to describe the cyclone efficiency with two parameters, Reynolds number and Stokes number. Stokes number is this criterion containing the particle size, and it contains also the size of the cyclone. In fact, the Stokes number is the ratio of a characteristic time of a particle compared to a characteristic time of the flow. And what is that characteristic time? Well, it could be the time needed for a particle to stop. If the flow turns, the particle for inertia will continue for some time straight, not following the gas completely. And then this the time that the particle flows on its own when the gas turns could be more or less the characteristic time. And the characteristic time of the flow could be the length of the flow times the divided by the velocity, for instance. So it is very vague, but it is how this is designed. I have copied this from some literature. It shows that, in fact, if you have a certain Reynolds number here, the Stokes number is no longer dependent on the Reynolds number, so it can be simplified. You could say that the efficiency of the cyclone for a certain particle size depends on Stokes number. And now it is where I want to skip, really. It is formulations of Muschelknautz. As I said, Muschelknautz was one of the top persons in cyclone theory, and he has written some very useful formulations, but they are very complicated and very difficult to understand, containing a number of different parameters, so many that you're a little suspicious. But when they do comparisons between different approaches, they found that Muschelknauf's approach is the best. So despite everything, it is worthwhile if you want to know more about the design of cyclones. You could look at the chapter in the VGB heat atlas, which is available in English. It was written in German originally, but it is available in English, heat atlas. And he has written a chapter there where he describes in detail how he thinks. Anyway, he comes to the conclusion that it depends on the Stokes number and also on the particle Stokes number. Just a moment. I am not sure about this. This must be the particle concentration. I think it is particle concentration. So it is particle concentration in the inlet to the particle concentration. This is a kind of dimensionless quantity. Same thing here. It is rather vague and not very satisfactory. So I think I should not bother you really with this. The conclusion can be given, and I have said this before, that in the boiler, when you have different powers of the boiler, different amounts of air, of gas, and the area is different, the barrel of the cyclone is affected also, and because it has to swallow this flow of gas with a certain typical velocity, so it has to be scaled up according to the power of the boiler, and then it becomes very large, too large to be efficient. And this is actually the conclusion of this. When the cyclone becomes too large, it's not very efficient. So this is why the solution is to have multiple cyclones. And yesterday I said that the typical maximum size is 8 to 9 meters for a cyclone. And if they cannot be bigger than that, so in that case, they have to be multiplied by several cyclones. That's all I think about this. Combustion scaling. In this case, it is not so much the horizontal direction. Yeah, for the introduction of fuel, it's the horizontal direction. But if you want to know about the reactions in your reactor, then it is the vertical direction, because it is the flow that carries the gas which may react in that direction. So you have the vertical Dampköhler number with the rate of reaction, the length of the riser, and the velocity times inlet concentration of the gas. And as I said before, this leads to some rather simple considerations regarding the reactor and the gas. Yeah, previously we were discussing concentrations. Here it is focused on the gas residence time. So they should be similar in two reactors. But also the number of turns in the cyclone should be similar. So one has to also consider the cyclone efficiencies and compare the cyclones to make the number of turns similar in the two reactors, because that is what gives the particle. This is gas residence time, and this is what gives the particle residence time. So this is also very important. I will show you a comparison that was made by two reactors. Now you recognize our reactor, and this was a typical laboratory scale reactor from the Technical University of Hamburg in Germany. It is a tube that goes up like this to a cyclone, which is very small, as you can see here, downcomer, and then a circulation loop like this. After the cyclone, there is this combustion chamber, a kind of reaction chamber, so it is an outlet where reactions can also take place before gas concentrations are measured in the outlet. Here the gas concentrations are also measured somewhere in the outlet. And the question is, yeah, these were not scaled, these reactors, they were just what they were. It was nothing to do about that. But we wanted to see how about the reactions in these reactors if we use the same fuels, the same temperatures, and the same bed material, etc., and almost the same residence times. So here is the data that we have had, and this is our Chalmers, and this is the German one, and there was another a commercial boiler in the small town of Flensburg in northern Germany. So we also compared the various data with this Flensburg boiler just to get an idea of the residence times that were available in various equipment. First of all, we have the volume of the combustion chamber. It was, as you can see, quite narrow racer. It is a small volume. We have a larger volume, of course, and in the commercial boiler, the volume was very much larger. We're also interested in the cyclone volume, very small in the German case, larger here, but very large than in the commercial boiler. We have the afterburner chamber. I mentioned the afterburner chamber here, and our afterburner chamber is this one, up to this point where the heat transfer surfaces start. So we have a particular space here where reactions could take place at the same temperature as in the combustion chamber. Well, we call this an afterburner chamber, and here it was added an afterburner chamber. So the volume of that was also of interest. Afterburner chamber. Of course, ours were much larger than this one. The gas residence time was 2.6 seconds here, 2.2 seconds in our case, and 3.8 seconds in the commercial boiler. Not too different. So here the scaling was rather reasonable, even though the volumes were different, but the length scales and velocities were adjusted such that we had reasonably similar residence times in the combustion chamber. And then we have some residence times in the cyclone. Of course, in this bigger cyclone, the time was bigger, but surprisingly enough, ours were rather similar here. And also in the afterburner combustion chamber, they made a rather big afterburner combustion chamber, so they had a longer residence time, whereas ours were smaller. And what we did then was we added these to the cyclone and the afterburner chamber, and we said that they were at least in the same order of magnitude as in the boiler, as in the cyclone of the boiler. So these two together were about the same as in the boiler. So then we had fulfilled, or at least approached, some kind of similarity here. So we tried to make some ratios of the residence times, and this is what we have. It's not perfect. And then you can see something about the results. of the combustion in these cases. We burnt coal, peat, and wood. This is Chalmers, and this is the German research equipment. And in this case, it was the CO, carbon monoxide. And in the case of wood, we had a high concentration initially of carbon monoxide, and then it declined like this, and it was zero, almost zero at the exit. With peat, with coal, for instance, to take the other extreme, we had some lower CO, and at the exit it was almost zero. At the more narrow riser, they didn't have any of these higher concentration in the bottom, but they had already from the bottom a much lower concentration. And I think this has to do with the mixing, the horizontal mixing. In the small case, the horizontal mixing was instantaneous, and combustion was more of the gases was more instantaneous than in this case, where you have some horizontal mixing that retarded the progress of combustion. But in any case, we ended up in a reasonable way. But here it was more efficient. Then we investigated also the nitric oxide, NO, and we found that for coal, which contains more nitrogen than the other fuels, we had a high concentration in the bottom, and then it falls because it is reduced by char, for instance, in the reactor, and it has a certain concentration at the exit. If we have wood, we have much less nitrogen in the wood, so the initial concentration will be much less here, but there's less reduction in the furnace because the char inventory is less, and the char inventory is what is reducing the nitrogen oxide. So here we have very little reduction, but still we have an emission which is about the same as in the coal case. But you see, the coal is, although it is potentially worse, it is better because it produces char, and the char loading in the case of coal is higher than the char loading in case of biofuels. In the narrow reactor, in the case of coal, we had something similar. We had very high initially, but even more steep reduction here, and we had a reduction to about almost the same level as that one. So you can see in short, I think there are many similarities between the reaction conditions in the two reactors, despite the great differences between them. But the narrower reactor was more efficient when we have such a carbon monoxide, because this is directly affected by the presence of oxygen, whereas the nitric oxide is reduced more slowly, perhaps in both cases, because it is dependent on the presence of char for the reduction of nitric oxide. But on the whole, the emissions were quite similar. Yeah, that was a kind of experience in scaling, not perfect scaling, but we try to compare two quite different units to see what happened. Yeah, this is also something that I would like to skip because we have not mentioned it before, but I can mention it superficially without going into detail too much. And this has to do bubbling bed scaling. We have not gone into the fluid dynamics of bubbling beds very much, and the interaction of bubbles and emulsion phase and so on. And this is what comes up here. But just to give a superficial view of the whole thing, I can go through it. So here we have scaling in the vertical direction, as I have shown before. This is the dimensionless form of this. But here we have to separate it into two phases. We have the particle phase, and we have the this is the bubble phase, and this is the particle phase. This is the emulsion phase. So in the bubble phase, we have a certain voidage because of the bubbles, and we have velocity that is the difference between, of course, the actual fluidization velocity and the minimum fluidization velocity. This is the minimum fluidization velocity is found in the particle phase, but if we subtract that, we get the difference between these in the rest of the reactor. And that here is the reduction then of the concentration from the bottom and onwards, because of a reaction that here takes place in the bubble phase, and it is a gas reaction only taking place in the bubble phase, in the voidage of the bubble phase. And here we have the interaction between the bubble phase and the emulsion phase. It looks like this, and it is minus here, but in the other equation, which is from the emulsion phase only, where you have a voidage of the emulsion phase, and according to the two-phase theory of fluidization, the velocity in the emulsion phase is minimum fluidization velocity, and the particle concentration in the emulsion phase is here, and also you have to subtract that one, which is the bubble phase. So here you get the amount of particles producing this reaction between the gas and solids, according to this formulation. But also here we have to consider the interaction between the bubbles and particle phase. So what was subtracted here is added here. This is an interaction term between the two equations, the bubble phase equation and the emulsion phase equation. You translate this into the dimensionless form. You get, of course, the Damköhler numbers, but you get a new number here, which is a number of transfer units, which accounts for the gas transfer between the bubbles and the emulsion phase. So it is something that happens along the reactor, and this is typical for heat exchangers and for chemical reactors. You have this number of transfer units. If you see the process here, you have in the emulsion phase, you have a certain this is height, this is concentration. Here you have a certain concentration in the emulsion phase, but it is in the bubble phase that reactions take place. So here it decreases from the inlet to the outlet situation, described by some final expression that you can get here, including both Damköhler and the number of transfer units. So the number of transfer units connects these two regions, because there is an interchange between the emulsion and the bubble phase according to this term. But and that is described by the number of transfer units. So this is very, this is how this type of modeling takes place. If you have a bubbling fluidized bed reactor, I don't think it is of interest for our case, maybe for gasifiers, but not for combustors, because of the much higher velocities, and we don't have so clean-cut bubbling conditions and bubbling bed. We have the splash zone and the whole circulating system. Finally, I will say a few words about the boiler scale up, and this is a historical view that here it started, the CFB started in this 1980, and in the beginning, of course, the small equipment, small boilers were manufactured, but gradually the maximum size, at least the red curve here, was increased. So the companies dared to gradually scale up their units because they wanted to come up to a large scale utility size unit. On the other hand, as you can see also from other many dots here, there were many curves, many plants that did not try to reach the absolute high level, and these plants were probably intended for industries or district heating systems and other more limited demands of heat and electricity. So this is one pattern, and they explain, the boiler companies explain how they were thinking in the scale up. They refer to various plants here. This is a 340 megawatt electric power plant looking like this. Then they had built another plant with a certain different configuration with the cyclones on both sides. And then they added the information they had from these two to build or to design. I don't know if they built it. They proposed this one. This was Alstom, boiler manufacturer. And they want to show the principle of how to scale up to a 60 megawatt electric power CFP with 6 cyclones in this way. They wanted to show that, yeah, we know this. We have full experience of this type of plant. We have full experience of this type, so we can sell this type. This is what they wanted to show when they published this information. The same thing here with Foster Wheeler. They have various plants, and you see the time of time they were put into operation. 2 cyclones in the beginning, and then scaled up still with 2 cyclones. But the other possibility was to use 4 cyclones, and so on. So this is what they want to show, that, yeah, we know this business, we can scale up without any problem. That's not necessarily true, but this is what they want to say. Here is another example. I don't know why I put this here. I just wanted to illustrate the various feed points from this side and from the rear side, also from the cyclone side. So there were 8 feed points to this about 235 megawatt electric power plant. Yeah, this one I have. This is another scale up aspect. This is the 300 megawatt plant electric power, and it looks like this. The dimensions are given here and here. It is made in this way, as I have explained before, in order to penetrate well the fuel and the secondary air. It is like this. But if they wanted to scale up this, they didn't want to add another plant here to make it twice as long and to have 6 cyclones on the same side. But instead they put the two of these plants together into one plant like this. Then automatically they got this pant leg bottom part, and they got some internal wall here which was opened. There was a wall, it is a wall, but it is opened for particles to move from one side to the other. So it is not completely closed. And then they put cyclones on both sides. There are 6 cyclones, but this means that there was not so much space for these wing wall heat exchangers, because the entrances to the cyclones takes a lot of place, and they had they could add a few internal wing wall surfaces, and then they could add some wall surfaces in this central part of the furnace, as I have shown before, and as is maybe indicated here. But the amount of surfaces, heat transfer surfaces in the furnace was not enough. There was not enough space. So they were obliged in this size to have external heat exchangers. This is nothing desirable because it is a complication, but it is, as you have seen before, it is possible, and it can be done. So it is, yeah, this again, I've shown this a couple of times. Lurgi type of external heat exchanger, very complicated, and they just control the amount of material by the valve here, and the rest goes back into the furnace. You can see here the pant leg, and inside these pants they have the injection points for air and for fuel. So they have it both on the outside if there is space and on the inside. So this means that the fuel will be better spread, and secondary air will be better spread here. In this Foster Wheeler design, they have a very special heat exchanger where they have one loop seal here, and then the heat exchanger is here, but it receives also bed material from the inside, and then there is a final loop seal here. So this is where the bed material returns to the bed. Now we can see clearly the wind boxes, one wind box for the main combustor and one wind box for this external heat exchanger. Here in the bottom here there are tubes. Nozzles. I mean nozzle. Here there are nozzles, and now you can see the tube that is bent to form the bottom. Then the tube goes down here around this bottom space and to this header. So there are tubes going straight to the header, but some tubes are bent away to form the bottom, and they form also the wind box. Same method was used here. Tubes come like this, bent away to the header, like here, like this. This is about, if we have a 600 megawatt boiler, we multiply by a little more than 3, and we get then 2000 megawatt thermal power. And I want to give this number 2000 thermal power for a very large boiler, comparing with the amount of power that can be extracted from such a heat exchanger, which is in the loop seal and which is rather limited. It's about 20 megawatt, according to Foster Wheeler. So it is 20 megawatt. It's not so much compared to 2000 megawatt. I think it is because of that they prefer to make many cyclones, 8 cyclones perhaps, instead of 6 cyclones. So they have they have space for more external heat exchangers in each loop seal. But they also try to extend this power by adding one heat exchanger on top of the other, like this. So the particles come from the cyclone first to this loop seal heat exchanger, and then it goes to this loop seal heat exchanger, which is similar to that one, and then back to the furnace. So then they could multiply them by 2, and they had about 40 megawatt thermal power heat that they could extract in this. In this type of heat exchangers, they can extract more if there is more circulating material, of course. It depends on the available heat coming from in the circulating material. Well, yeah, this is another comparison. I don't think this is very interesting. A few years ago, they said they wanted to make 800 and this manufacturer for 500 to 600, and they said that they will use a rather high pressure. This is supercritical pressure and supercritical temperatures of the steam to get a very high efficiency. This manufacturer wanted to have 8 cyclones, and this one 6 cyclones. And in fact, this was Foster Wheeler, so they had this Intrex with 10 to 20 megawatt each, and then they could have 8 such devices with 2 in series. This was what I showed you on the previous figure. Whereas here they don't give any information in the boiler manufacturer. Okay. I think this is it. I come to the conclusion, and time is also concluded. So I can conclude what I have said before. I have said that strictly formal scaling is impossible in practice, but fluid dynamic scaling can be made making a compromise, and this is very useful to represent the flow patterns of hot large-scale boilers in a cold small-scale test rig. And I showed our experiment, and I showed you the video, which is also a manifestation of such a scaling. The combustion scaling is a little different. Then much information is already available, because the same temperatures and excess air and fuel and so on can be used as in the large scale, and only the height the height can be scaled. The horizontal scaling is more difficult because of the dimensions, but the vertical scaling can be, as I have shown, by the height and the residence time. The influence of cyclone operation is also it has not been well stated in the literature, but it is, of course, important if you want to investigate the vertical combustion scaling of how char particles burn out. Then you need to have a good scaling of the cyclone to compare the big cyclone in the commercial scale with a presumably smaller cyclone that you can have in the laboratory reactor. And then finally, the boiler scaling is done by the boiler manufacturers, and they use the building stones from similar scales that are then duplicated to obtain larger scales. This is not as simple as they want to pretend it to be, but it can be done with consideration of various minor complications. So this is it about scaling. Yeah, the literature. Glicksman is where you find the fluid dynamic scaling. Very good explanation to the details of scaling. So I would like to refer to this. And here you have the Dammköhler work, publication 1936, unfortunately in German. But if you have a translation program, perhaps you can translate it. It's very good, and it's a remarkable also piece of work. Then we have some reactor scaling here and some boiler scaling. And finally, we have our work here with fluid dynamic scaling, which was presented on a conference. And we also published in Fuel some work on scale up of fluid spread combustion, some kind of review paper. Finally, we have a paper on cyclones. This is a book on cyclones. I like this book very much, and it's very easy to read and very straightforward and easy to understand, comprehensive. But There is nothing about high-loaded cyclones, unfortunately. But if you want to know something about cyclones in general, I can recommend this book. About the fluidized bed cyclones, I have already referred to Muschelknauts, but I have not included it here. I have forgotten that. So, but I've given the reference to Heat Atlas. And yeah, I think, yeah, this is just some things that I have removed. That's too much. And we came to the end,